For decades, humanity has been locked in an unrelenting pursuit, building ever larger, ever more powerful telescopes in the hope of seeing further into the cosmos. Glass ground to extraordinary precision. Mirrors the size of buildings. And yet, for all our ingenuity, we are approaching the limits of what steel and optics alone can achieve. But what if the most powerful telescope ever conceived requires no mirror, no lens, no human hand to grind it into shape? What if it has been waiting for us all along, forged not in a factory, but in the furnace of a star? This is the story of a radical idea. One that dares to bend the very laws of physics to our will. There is a question that has haunted our species since the first human being raised their eyes to a clear night sky and wondered at the darkness between the stars. Are we alone? The universe stretches across distances so vast as to be almost meaningless to the human mind. And yet, silence. No signal. No visitor. No answer. It is possible, of course, that we have simply not looked closely enough. Even our most advanced instruments, the great observatories perched on mountain summits, the satellites drifting in the cold void above our atmosphere, can do no more than reduce a distant world to a single, faint point of light. A solitary pixel. A suggestion, nothing more. And yet, what we wish to see is so much more than that. Continents. Oceans. The slow drift of clouds across an alien sky. Perhaps, and here the imagination strains, the unmistakable geometry of city lights blazing on a world that does not belong to us. To achieve such resolution with a conventional telescope, one would require a mirror the size of the entire Earth. It is, by any reasonable measure, impossible. Which is precisely why a brilliant group of scientists has turned to something far more audacious. Rather than build an impossible telescope, they propose to use one that already exists. Our Sun. To understand how this might work, one must first grapple with a discovery that overturned everything we thought we knew about the nature of space itself. In the early years of the 20th century, Albert Einstein revealed that space and time are not separate things. They are woven together into a single, four-dimensional fabric, what physicists call space-time. And crucially, this fabric is not rigid. It bends. It curves. It warps in the presence of mass. Imagine, for a moment, placing a heavy ball upon a stretched rubber sheet. The sheet sags beneath the weight. Anything rolling nearby will follow that curve, drawn inward by the depression. Our Sun does precisely this to the fabric of space-time, on a scale almost beyond imagining. And light, traveling at the cosmic speed limit across the universe, must follow those curves. When the light from a distant world passes close to our Sun, it bends. It curves around the star. And when light bends around an object with sufficient mass, something remarkable happens. It focuses. This phenomenon is known as gravitational lensing, and it transforms our Sun into something extraordinary, a natural telescope of breathtaking power. The Sun's gravity can amplify the light from a distant world by a factor of 100 billion. A single, lonely pixel of light, transformed into a rich, detailed image containing tens of thousands of pixels. The physics is unimpeachable. The principle is sound. And the potential is almost beyond words. But there is, as there so often is in great human endeavors, a catch. The focal point, that precise location where all that gloriously amplified light converges, lies at a staggering distance from our Sun. To place a telescope at that focal point, to receive that precious image, a spacecraft would need to travel at least 650 astronomical units from the Sun. 1 astronomical unit is the distance from the Earth to the Sun, approximately 150 million kilometers. We are speaking, then, of a journey 650 times greater than that. To place this in perspective, consider Voyager 1, humanity's most distant emissary, launched in 1977 and still traveling to this day. After more than 4 decades of flight, Voyager has reached approximately 156 astronomical units. the destination we require is more than 4 times further still. With the rockets available to us today, such a journey would take not decades, but thousands of years. The civilization that launched the spacecraft would be dust long before it arrived. And so, if this mission is to be accomplished within a human lifetime, within, say, 20 to 25 years, an entirely new order of speed is required. Roughly 154 kilometers per second. A velocity that makes our fastest existing spacecraft look, by comparison, almost stationary. There are, at present, 2 serious candidates for the propulsion system that might achieve this. The first is the solar sail. Rather than burning fuel, a solar sail harvests the gentle but relentless pressure of sunlight itself. Photons, massless but possessed of momentum, push against an enormous, gossamer-thin reflective surface, driving the spacecraft forward through the void. To achieve the velocities required, a solar sail would need to perform what engineers call a photonic assist, a daring, dangerous dive close to the surface of the Sun itself. The closer the sail ventures to the star, the more intense the sunlight, and the greater the push it receives. A trade-off of extraordinary precision, proximity purchased with the constant threat of destruction. The engineering challenges are formidable. Such a sail would need to span an area equivalent to a dozen football pitches, yet weigh almost nothing. It would be exposed to temperatures sufficient to melt most metals. And nothing of this scale has ever been deployed in space. The second candidate is nuclear electric propulsion. Here, a compact fission reactor generates electricity to power highly efficient ion thrusters, engines that produce only a gentle thrust, but can sustain that thrust for years, even decades, steadily accelerating the spacecraft to extraordinary velocities. And crucially, when the spacecraft finally reaches the outer solar system, where sunlight is too weak to power conventional solar panels, the reactor continues to provide energy for the instruments on board. In isolation, nuclear electric propulsion is the patient tortoise of the race, slow to reach full speed. But combined with a powerful conventional rocket launch, the 2 approaches become complementary. A mighty initial kick from a chemical rocket, followed by years of steady nuclear acceleration, might just compress that journey into something achievable within a generation. Neither approach is ready. Both demand technological advances that do not yet exist. But neither, crucially, demands a miracle. Only exceptional engineering, exceptional patience, and exceptional will. And so we return, finally, to the question that makes all of this worthwhile. What, precisely, would we see? We would go from knowing a planet exists, a whisper of gravitational influence, a faint dimming of distant starlight, to mapping its surface in features just 10 kilometers across. In a matter of months, we could assemble a complete portrait of another world, a task that would take a conventional telescope longer than the current age of the universe to accomplish. We might see weather. The slow churn of storm systems crossing an ocean. We might see seasons, the greening of a hemisphere as its star climbs higher, the browning of another as the light fades. And perhaps, against the darkened face of that world turned away from its sun, we might detect a pattern of light that no geological process could explain. The faint, unmistakable grid of a civilization. This mission, still a concept, still a dream on the boundary of possibility, represents something more than a feat of engineering. It is a test of what kind of species we choose to be. Whether we are content to glimpse the universe from a distance, or whether we possess the ambition, the courage, and the patience to truly look. The telescope we need already exists. It has existed for 4.5 billion years, waiting in the mathematics of curved spacetime for a species curious enough to use it. The only question that remains is this. If we could finally see, what would we dare to find?